Hi everyone. So we're just going to jump right into this with question 1. It says the equilibrium constant is given for one of the reactions below. Determining the missing equilibrium constant. So in the first reaction we have 2SO2 plus O2 yields 2SO3. Now what we want to do is we want to see what's different about the second reaction where we don't know the Kc. So the first reaction we do know the Kc, and the second reaction we don't. Well, there's two things that I can see here that are different. The first thing is, if we look here, SO3 is the product, and over here SO3 is the reactant, and the SO2 and the O2 are the reactants, and over here the O2 and the SO2 are the products. So this thing has been reversed. The other thing that we can see is that here we have 2, 1, and 2, and here we have 1, a half, and 1. So it's also halved. So this reaction is reverse and half of this reaction. So what do we do to the Kc? Well, in order to find the new Kc value, so the Kc of the new reaction, or the second or the bottom reaction, equals 1 over Kc. I'm going to call this old. Okay, why is it 1 over? Because we reversed the reactions. So instead of products over reactants, it's reactants over products, or we take the reciprocal. But it's also half, so we need to raise this thing to the 1/2 power, or simply take the square root of it. So it's 1 over the square root of 1.7 times 10 to the 6th. And when you do that, 1 over the square root of 1.7 times 10 to the 6th gives you 7.7 times 10 to the negative 4, which is choice letter E. Alright, number 2 says, the reaction below has a Kp value of 3.3 times 10 to the negative 5. What is the value of Kc for this reaction at 700 Kelvin? So, if you recall, Kp equals Kc times RT to the delta N, where delta N equals NF minus Ni. N is moles, and in this case Kp is pressure and Kc is molarity, basically. So basically we're looking for the change in number of moles of gas. So notice if things were not gases, in this case they're all gases, so it's just changed in the number of moles. But if something was not a gas, it would not count as moles. So let's take a look here. The final state, or the products state, we have 2 moles of SO2 and 1 mole of O2 for a total of 2 plus 1, which is 3 moles of gas. So it's going to be 3 minus, if we look at the reactant side, we have 2 SO3 and that's it, so 2 moles of gas, which equals 1 mole of gas, which is changing. Now we need to rearrange this, because in this case we're given the Kp, and we're asked for the Kc. So we have to divide both sides by RT to the delta N. And we find that Kc equals Kp divided by RT to the delta N. Okay, like that. So we already found delta N. That's going to be 1. So what are we going to do? Well, we're going to plug in our Kp, which is 3.3 times 10 to the minus 5. We're going to plug in our R value, which is going to be 0.08206. This is liter atmospheres per mole K, okay, times our temperature, which is going to be 700 K. I didn't write in the liter atmospheres, mole K. Multiply, and then all to the delta N, which in this case is just 1. When you do that math, you find that Kc is equal to 5.7 times 10 to the negative 7, that's a 7, which is choice letter C. Alright, so if you haven't watched the previous question, please start with that one. But it says, in which of the following reactions will Kc equal Kp? So remember from the previous one, Kp equals Kc times RT to the delta N. Note that if delta N is 0, RT to the 0 will just be 1. So if delta N equals 0, Kp equals Kc. Why? Because RT to the 0 is 1, so Kp equals Kc times 1, so Kp equals Kc. Remember that delta N is the moles of gas. If you have things in here that are not gases, then that's not going to work. So let's take this example. All right, I'm just going to put when on here. When delta n equals 0, Kp equals Kc. So let's take a look. Here we have 2 plus 6, which is 8 moles of gas on our product side, minus 4 plus 7, or 3, which is 7 moles of gas on this side. So we have 2 and 6 is 8, and 4 and 3 is 7. Delta n is not equal to 0, so therefore we are not going to have Kp equal to Kc. Let's take the next case. We have 2 plus 1, which is 3, and over here we only have 2. 3 is not equal to 2, so that's not going to work. Here we have 2 plus 1, which is 3, and then only 2 over here. 3 is not equal to 2, so that doesn't work. Let's check the last one. We have 1 plus 1, which is 2, and then we have 1 plus 1, which is 2. So we have 2 moles of gas on both sides. So since we have 2 moles of gas on both sides, the delta n is going to be equal to 0, and Kp will equal to Kc. Alright, number 4 says, determine the value of Kc for the following reactions if the equilibrium concentrations of HCl is 0.13, HI is 5.6 times 10 to the minus 19, and Cl2 is 0.0019. So let's take a look at this. Well, the first thing we do is we have the reaction here, so we want to write the Kc expression. Remember that in the Kc expression, we're only putting things that are gases or aqueous, so in this case we're going to leave out iodine. So it's going to be products over reactants. So in this case, it's going to be the concentration of HI squared times the concentration of Cl2 divided by the concentration of HCl squared. Okay, so this is going to be our values. Since we are given equilibrium concentrations, we don't need to fill this into the ICE table or anything like that. We can just plug in the values directly. So if we look here, we're going to take the concentration of HI, which is provided to us, which is very, very small, so 5.6 times 10 to the minus 16, and we're going to take that and square it. We're going to multiply that times the concentration of Cl minus, which in this case is 0.0019. We're going to take that and we're going to divide it by the HCl squared, and you'll notice the HCl relative to the other two is much higher. It's going to be 0.13 squared. Alright, so if we look here, the products are clearly favored. There's very, very small, the reactants are clearly favored. There's very, very small amounts of products on the top and a much larger amount of reactant on the bottom. So when we do this, we get 3.5 times 10 to the negative 32. So what you see is we have a very, very, very small value of Kc. It's much, much less than 1, right? 10 to the negative 32, it's basically 0. Alright, so this means that the reactants are favored here because the reactants are going to have a much higher concentration than the products. So that's why we have a very, very small value of Kc, but that doesn't ask us that, it just asks us for the value. The answer here is choice letter D. Alright, this one is very similar to the previous one. It says, consider the following reaction, equilibrium concentrations, and the equilibrium constant at a particular temperature. Determine the equilibrium concentration of H2O. In the previous case, we had to find Kc given equilibrium concentrations. In this case, we're given Kc and some equilibrium concentrations, and we need to find the other one. So the first thing we need to do is write the Kc expression. So remember that Kc is products over reactants. So in this case, the concentration of C2H5OH, ethanol, on the top, over the concentration of C2H2 ethylene, C2H4 ethylene, over times the concentration of H2O. So it's, in this case, they're all 1, so no exponents here, they're all 1, and they're all gases are aqueous, so they all go in the equilibrium expression. In this case, we're looking for concentration of H2O. So what we want to do is plug in what we know. Well, we know Kc. 9 times 10 to the 3 is Kc, so I'm just going to plug that in. Equals the concentration of ethanol at equilibrium. This is important. 1.69. Okay, we don't need to use an ICE table because these are not initial concentrations, they're equilibrium concentrations. The concentration of ethylene is 0.15. Sorry, 0.015. That's, you can see that. All right, and then the concentration of water is what we're looking for. That's the unknown. Well, how do you do this? Well, the first thing you want to do is cross multiply. So 9 times 10 to the 3, 9,000 times 0.015, okay? And when you do that, you get 135 times the concentration of H2O, because that cross multiplies as well, so that's going to cross multiply through as well, equals 1.69. So that is basically just equal to that. Now you're going to divide both sides by 135, and you're going to get the concentration of H2O is equal to, where is it here? 0.013 molar, which is choice letter B. Alright, so if the previous problems weren't completely on the screen, I apologize about that. I have tried to zoom out a little bit, so now this is roughly as wide as my paper, so I can't possibly do that again without writing on the table, so hopefully that'll work out. Alright, it says, consider the following reaction. COCl2 gas is in equilibrium with CO and Cl2. The reaction mixture initially contains 1.6 molar COCl2. Determine the equilibrium concentration of CO if Kc for the reaction is 8.33 times 10 to the minus 4. Calculate this based on the assumption that this answer is negligible compared to 1.6 molar. So I just rewrote the reaction down here. Here we're going to need an ice table. Why do we need an ice table here and not in the previous case? Because in this case we're given the initial concentrations. In the previous two problems we were given the equilibrium concentrations. When you're given the initial concentrations, you have to use an ice table. So we're going to use initial, change, and equilibrium. Let's plug in what we know. Well, we know that the initial concentration of the COCl2 is 1.6 molar. Okay, we can also assume that the initial concentrations of these things are 0, because we start with initially just this, and then it reaches equilibrium, so it makes some of this and some of this. We want to know what's the change. Well, this is all 1 to 1, which is helpful. So we're going to subtract x amount of this, we're going to gain x amount of this, and gain x amount of that. When we have equilibrium, we're simply just going to do the math. So this one's going to be 1.6 minus x, but we are going to ignore this x, so we don't have to use the quadratic equation, and because we just look at the answers, they're way small compared to 1.6. They're way less than 5% of this value. Okay, these are all very small numbers. All right. It also tells us we can ignore this. In this case, you have 0 plus x, which is just x, and in this case, you have 0 plus x, which of course also is just x. Now we just write our Kc expression. All right, products over reactants. In this case, everything's a gas, so it all goes in there. So our first product is the CO. Our second product is the Cl2, and our reactant is COCl2, and they're all in brackets because we want the concentrations. Now let's plug in what we know. Well, we know Kc. Okay, it's 8.33 times 10 to the negative 4 equals these. We know, well, they're x's, x times x, which is just x squared, divided by this one, which is not 1.6 minus x, it's just 1.6 molar. Cross multiply, and we find that x squared is equal to this times 1.6, which is going to be equal to 0.00133. Take the square root of both sides, you can ignore the negative answer, and you find that x is equal to 3.7 times 10 to the minus 3 molar. This is the equilibrium concentration of CO. No, in this case, it also happens to be the equilibrium concentration of Cl2 because they're 1 to 1. So the answer here is going to be, all right, I apologize about that. I made a small mistake here. This should be 3.7 times 10 to the minus 2. Okay, which matches our answer here, which is choice letter B. I don't know why I wrote minus 3 on my paper here, but it should be negative 2 as the answer. All right, number 7 says, consider the following reaction at equilibrium. What effect will increasing the pressure of the reaction mixture have on the system? So if we look here, we have a solid and a gas, and a solid and a gas. So if we look at the gases, because the pressure is only going to affect the gases, we have 1 mole of gas on our reactant side, and we have 1 mole of gas on our product side. Specifically, the O2 is the 1 mole of gas on this side, and the SO2 is the 1 mole of gas on this side. So there's an equal amount of gas on each side. So what does a reaction do? Well, Le Chatelier's principle, which is what this question is asking about, tells us that the reaction will shift to minimize disturbances in equilibrium. So if you increase the pressure on a reaction where there's 2 moles of gas on this side and only 1 mole of gas on this side, the reaction will shift to decrease the pressure. So if there's 2 moles of gas over here and only 1 mole of gas over here, the only way the reaction can decrease the pressure when you artificially increase it is to make less moles of gas, so it'll shift in this direction. But in this case, this reaction actually can't solve this problem. It has no way to do that. So basically, if you increase the pressure, no effect could be observed. Why? Because it has no way to get rid of moles of gas. If it had a way to get rid of moles of gas, when you increase the pressure, it would do that. But because both sides have 1 mole of gas, there is going to be no change in the no effect will be observed in the reaction here because there's 1 mole of gas on both sides. All right, question 8, it's more of the same on Le Chatelier's principle. It says the following reaction is exothermic. What change will shift the equilibrium to the left? All right, so we want to shift the equilibrium in this direction to the left. Well, if this reaction is exothermic, we can think of heat as a product. Okay, we can think of heat as a product of the reaction because the reaction is giving off heat, so we can think of heat as a product. Well, Le Chatelier's principle says that the reaction will do what it can to disturb or to reestablish equilibrium. So if you increase the temperature, this reaction is going to want to get rid of that heat. It will get rid of that heat by shifting it in this direction. So increasing the temperature will shift the reaction in this direction. Okay, now let's see, so that's choice letter C. Let's see what will happen if we do A or B, because all of the above is an answer. So raising the temperature will shift it this way because the reaction wants to get rid of heat, and heat is a product in an exothermic reaction. What about removing O2? If we remove O2, the reaction will say, hey, there's not enough O2 in the system. We need to make more O2. Well, what's the only way that the reaction can make more O2? It's by decomposing the SO3 into SO2 and O2, or said another way, shifting to the left. So we talked about that one. This one will also cause the reaction to shift to the left. What about adding SO3? Well, if we add SO3, the reaction says, hey, there's too much SO3. How do I get rid of SO3? Well, I turn it into SO2 and O2, or said another way, I shift the reaction to the left. So all of these answers will shift the reaction to the left. So the answer here is D, all of the above. All right, it says consider the following reaction at equilibrium. What effect will removing NO2 have on the system? So the concentration of NO2 is going to decrease artificially. Well, Le Chatelier's principle tells us the reaction is going to do what it can to minimize the disturbance in equilibrium. So what the reaction says is, hey, there's not enough NO2 in the system because someone took out some of the NO2. Well, what's the only way the reaction can make more NO2 to compensate for the NO2 that is gone? Is to shift to the left, because it knows that if it reacts SO3 with NO, it can make more NO2 to replace what has been lost, okay, or taken out. So in this case, the reaction will shift in the direction of the reactants, which is to the left, because it wants to make NO2 when the concentration of NO2 is artificially decreased. So in the past 3 problems, we've talked about Le Chatelier's principle, and the major thing to remember is that whatever is artificially done to the equilibrium reaction will do what it can to restore order or restore equilibrium, or replace what is missing, or get rid of what is put in excess, or whatever the case may be. All right, number 10 says, which of the following is not a conjugate acid-base pair? So we have H2O, H2SO3, and we have HSO3 minus. So if we were to take an example of H2SO3 aqueous, and we were to add it to H2O liquid, this would be an equilibrium with If this is an acid, sulfurous acid, it's going to protonate the water. It's a proton donor. So what we end up with is H3O plus aqueous plus HSO3 minus aqueous. So this lost an H plus. So it was neutral here. Now it's minus because it lost an H plus. This gained an H plus. It was H2 here. Now it's H3 and it has a positive charge. You got to remember the charges. This is the acid, okay, and this is the conjugate base. This is a conjugate acid-base pair. If you were to look at this one, you have NH4 plus and NH3. If you take NH3 plus H2O, NH3 acts like a base. The conjugate acid has one more H and a positive charge. So therefore, this is a conjugate acid-base pair. If you want to think about it the other way, this is the acid. When it loses an H plus, it has one less H, and it went from plus to neutral. All right, in this case, we have acetate and acetic acid. This is a conjugate acid-base pair that you actually are going to use in the lab. Okay, in this case, this is the conjugate base. When it gains the H plus, you have the extra H, and it went from negative to neutral. Or if you want to look at it the other way, in this case, this is the acid. It loses an H plus, so it loses the H, right? It has one less H, and it now has a negative charge instead of a neutral charge because it loses H plus. If we look at H3O plus and OH minus, these are not a conjugate acid-base pair. Why? This has three H's. This only has one H. So because this has three H's and this only has one H, it has not lost an H plus. Okay, it's actually lost two H pluses to get to here. That makes them not a conjugate acid-base pair, and that makes the answer here choice letter D. All right, so we're looking for the conjugate acid of HCO3 minus. So we want HCO3 minus to act like a base. So if we take HCO3 minus aqueous and we react it with water, we want it to act like a base. So when it acts like a base, it gains a proton. Okay, note that that's an H and a plus. All right, so if we want to find the conjugate acid of this, it has to behave like a base. So it's not H1, it's now H2CO3. This, you'll note, was minus. It gains an H plus from water. So it's not only got an extra H, but the minus and the plus cancel out such that you have a neutral species, which is aqueous. Now, after the H2O loses that proton, you find its conjugate base, which is OH minus, which is also aqueous. Okay, so in this case, this acts like a base. Okay, and gains a proton from this. So this, if you will, is a base, and this is its conjugate acid. All right, so the answer here is H2CO3, which is choice letter B. Note that you could also draw the conjugate base of this where it would act like an acid and protonate the water to make H3O plus, and you'd end up with CO3 2 minus. So this one's so-called amphoteric because it can go both ways, but that's not for this question. That's just an extra piece of information for watching the video. All right, question 12 says, give the characteristics of a strong acid. So I'm just going to write a strong acid, HCl aqueous plus H2O. You'll notice that this one is not equilibrium. This just completely protonates this, and what you end up with is H3O plus aqueous plus Cl minus aqueous. This is just one example of a strong acid. There are 6 or 7 or 8 strong acids, depending on how many you learned. But basically, this is just one example. So this completely protonates it. If you remember the previous example, this was an equilibrium reaction. This happened to be a base and not an acid, but it was an equilibrium reaction. This is not really an equilibrium reaction. This is just basically it protonates the water. So let's look at the first thing. The first thing is, has an equilibrium far to the right. That's another way of saying it's not an equilibrium reaction. It means it basically just forms products, okay? Far to the right means it strongly favors the products, so strongly that we say it's not even an equilibrium reaction, probably. All right, has a polar bond. The HCl bond is definitely a polar bond. If you remember back to your Gen Chem 1 and your Lewis structures, the HCl bond is a very polar bond. Why? Because chlorine is far far more electronegative than hydrogen. So chlorine is delta minus and hydrogen is delta plus. Ionizes completely in aqueous solution. That's another way of saying this is not an equilibrium reaction. It completely forms H3O plus and Cl minus. That means ionizes completely. Has a weaker bond to hydrogen. This has a very weak bond to hydrogen. It desperately wants to get rid of a hydrogen to the extent that it completely does it when you put it into water. So this has a very weak bond to hydrogen. So the answer here is choice letter E, which is all of the above. It's very important to remember that strong acids are not forming equilibrium solutions in water. They're completely ionizing in water. So said another way, if you had 0.1 molar HCl, you would have 0.1 molar H3O plus, which could actually allow us to calculate the pH of the solution, as will be done in a future question. I don't know if it's HCl in the future question, but it's a strong acid. All right, number 13 says, which of the following compounds will result in acidic solution when dissolved in water? Well, if you draw KCl in water, in the previous one I showed you HCl is a strong acid. This means that Cl minus is an incredibly weak base. So this is going to end up with a neutral solution. All right, what about NH4Cl? Well, effectively for B, what you have is NH4 plus aqueous. If you'll remember, this is the conjugate acid of NH3. If we add this to water, what's going to happen is you're actually going to protonate the water. And you're going to end up with H3O plus. Okay, so it gives the H to this, plus NH3, the conjugate base. And this would be an equilibrium reaction. But when you add this NH4 plus to water, note that chloride is just the counter ion, so it's basically just a spectator ion. The NH4 plus acts as an acid, thereby increasing the concentration of H3O plus, thereby forming an acidic solution. What about letter C? Well, in letter C, we have Na2CO3. Again, the NAs are just spectator ions. So what we effectively have is CO3 2 minus aqueous. Okay, this is the conjugate base of H2CO3 carbonic acid, the second conjugate base, but it is definitely basic. If we add this to H2O liquid, it's not going to give a proton. Clearly it doesn't have a proton to give, but it's not able to give a proton. It's going to accept a proton, and what you're going to end up with is HCO3 minus aqueous plus OH minus aqueous. What's going to happen? You're going to increase the concentration of OH minus in solution. This one is actually going to be a base. Okay, let's look at the last one, NaF. Again, we have a spectator ion, the Na. So when we have NaF, what we effectively have in solution is F minus, with Na being a spectator ion. We add that to H2O. You'll remember that F minus is the conjugate base of the weak acid HF. This again does not have a proton to give, so it's going to accept the proton, and what you end up with is HF aqueous, which is a weak acid. Note that if you have Cl minus, you make HCl, which is a strong acid, and it's not an equilibrium reaction. That's why this one's completely neutral. But in this case, you make HF, which is a weak acid, plus OH minus, because you had to gain that proton. Again, you've increased the concentration of OH minus in solution by adding both of these things, making this a slightly basic solution. So the NH4Cl is the only one here that's going to end up with H3O plus, extra H3O plus in solution. So it's the only one here that's acidic. All right, number 14 says, which of the following solutions would have the lowest pH? Assume they're all 0.1 molar and acid at 25 degrees C, and then the Ka values are below. So here I just wrote out an example of HA. Okay, we have B, C, and D, and E. It doesn't matter though. We could call this B, C, D, and E. It doesn't matter. So HA is a weak acid. It reacts with H2O. It donates a proton to H2O to increase the concentration of H3O plus in solution, making the solution more acidic, and then we get A minus. All right, the Ka is products over reactants, concentration H3O plus, concentration A minus over concentration HA. Well, which one of these things affects the pH? Okay, so the lowest pH means basically the highest concentration of H3O plus. So the H3O plus is what affects the pH. So if the H3O plus concentration is high, the Ka value will also be high. Why? Because Ka, it's just another K, it's products over reactants. Um, since H3O plus is a product, a high value of H3O plus or a low pH or a stronger acid is going to have a lower Ka value because it's on the top. Note that if it were on the bottom, then it would be the opposite, but it's not on the bottom, it's on the top. So the H3O plus is what we care about. The H3O plus is on the top. Since we have a higher H3O plus value, we're going to have a lower Ka value. Okay, excuse me, a higher Ka value. So which one of these has the highest Ka? First, you want to look at the exponents. Only look at the number out here if the exponents are tied. 10 to the negative 2 is a much larger value than 10 to the minus 8, right? This is 0.0000 with 8 zeros before you get to the 8. Maybe 7 zeros before you get to the 8. This one is 1 0 before you get to the 6, okay? So this is 0.067, okay? So that's going to be 6.7 times 10 to the minus 2. This one is 0.123456788. So I'm just looking at the extremes. This is a much larger number than this. So if you have a negative 2, it's going to be a much larger number than negative 8. Note that if there were two answers where they're to the negative 2, then you'd look at this number, and whichever one's the biggest number is the biggest number. All right, 9 times 10 to the negative 2 is a bigger number than 1 times 10 to the negative 2. But in this case, the exponents are different, so the answer here is choice letter E. All right, so if you haven't already watched the previous question, do that because this is exactly the same thing. It says, which of the following is the strongest base? The base is followed by the Kb value. So in the case of a base, these are a bunch of different nitrogen-containing organic bases, many of them, except ammonia. You have B minus plus H2O yields Hb plus OH minus. The thing that affects the pH is the OH minus. So the one with the greatest concentration in OH minus is going to be the strongest base. Again, since OH minus is on the top, the one with the greatest Kb value is going to be the one with the that's the strongest base. So if you look here, first look at the exponents. Okay, negative 4 is the largest value. And then if you have a tie, then it's just whichever one's the larger number. So 8.6 times 10 to the minus 4 is bigger than 4.4 times 10 to the minus 4 because 8.6 is bigger than 4.4. But note, that's only when you have a tie in the exponents. If you're minus 5 or minus 9 or minus 10, these are all much smaller numbers. All right, I haven't here gone over the pKa or the pKb, and I can't remember if that question comes up after this or if that was on the homework. But note that you should know this in terms of pKa and pKb as well. So the smaller the number for the pKa, the stronger the acid. Because if you take the negative log of this thing, then this one is going to be 3 point something, and this one is going to be 9 point something. So here the pKb equals 9 point whatever, okay, and here the pKb equals 3 point whatever. All right, I don't know the exact values because I didn't calculate them. So the smaller pKb is going to be the stronger base, or the smaller pKa is going to be the stronger base. Number 16 says, which of the following acids will have the strongest conjugate base? Well, if you look at these acids here, these ones are all strong acids. So their conjugate bases are going to be neutral because they're strong acids, which means that if you have these things in solution, I'm going to take HBr as my example here, aqueous, and we add it to H2O liquid, it's not an equilibrium reaction. You end up with H3O plus aqueous plus Br minus aqueous. So what's happening here? All right, what's happening is you have complete ionizations. Another way, whatever the concentration of HBr is, it's the same concentration of H3O plus. Another way of saying this is Br minus has zero interest in reacting with H3O plus. This is not an equilibrium. This is not going in this direction. Why? Because this is an incredibly weak base. It doesn't even want to take a proton away from H3O plus, which is very acidic. All right, so this is a very, very weak base. But let's take a case of the HF. So if we take a weak acid, okay, the weak acid is going to be HF. And if we have HF aqueous plus H2O liquid, what's going to happen? This is going to form an equilibrium reaction, and you're going to end up with H3O plus aqueous plus F minus aqueous. All right, what does this mean? It means, to some extent, this is going in the other direction. Said another way, F minus is able to take away protons. It can take away protons from H2O, but it can also take away protons from H3O plus. So the reaction is able to go in this direction because this is a much stronger base than this, or Cl minus, or NO3 minus, or I minus. I just wrote the top one, or the first one, but it applies to all the other ones. Since this is a weak acid, its conjugate base is a far stronger base. In fact, this is not a base at all. This would just give you a neutral solution. All right, number 17 says, calculate the concentration of OH minus in a solution that contains 3.9 times 10 to the minus 4 molar H3O plus at 25 degrees C. Identify the solution as acidic, basic, or neutral. So if we take a look at this, this number is greater than 1 times 10 to the negative 7 molar. So that means your solution is acidic. All right. When a solution has H3O plus of equal to 1 times 10 to the minus 7 molar, that means the solution is neutral. But when it's greater than 1 times 10 to the minus 7, it means the solution is acidic. I'm not going to go into great detail on that here, but there are several videos from the homework where that is gone into in much greater detail. So the Kw equals the concentration of H3O plus times the concentration of OH minus. Okay. So if you basically, Kw is a constant, 1 times 10 to the minus 14, if you divide the one that you have into 1 times 10 to the minus 14, you'll get the other one. In this case, we have the H3O plus concentration, and we want the OH minus concentration, so the concentration of OH minus equals the Kw divided by the H3O plus, but it works the other way as well. The H3O plus equals the Kw divided by the OH minus, so it's 1 times 10 to the minus 14 divided by 3.9 times 10 to the negative 4. And when you do that math, you find that it's 2.6 times 10 to the minus 11. Okay, so this is the concentration of the OH minus. You'll notice that that's 2 of the answers. So we also need to identify whether it's acidic or basic. We already talked about this. It's acidic, so the answer here is choice letter D. All right, it says determine the pH of 0.00598 molar per chloric acid. Hopefully you've had this one. This is a strong acid. This would be the same thing if this was HCl or HBr. HClO4, aqueous, or several others, plus H2O, liquid, as I've written in several other questions. This is a strong acid. It's not at equilibrium. It forms H3O plus, aqueous, plus ClO4 minus, aqueous. All right, so this is a strong acid. Note that if this is 0.00598 molar, this is also 0.00598 molar because it completely reacts with water to form this. And for every 1 molar of this, you get 1 molar of this, so they're going to be equal. So the pH equals the negative log of the concentration of H3O plus, which is going to equal the negative log of 0.00598 molar. Note that this is 5.98 times 10 to the minus 3. So the pH, since it's minus 3, is going to be 2 point something, because if it's 1 times 10 to the minus 3, the pH would be 3, but it's going to be 2 point something without doing any of the math. You can figure out which answer it is, but in this case, it's 2.223 is the pH, which is choice letter D, because it's 5.98 times 10 to the minus 3, and the log of 1 times 10 to the minus 3 is 3. The log of 5.98 times 10 to the minus 3 has to be 2 point something. All right, number 19 says, determine the pH of a 0.461 molar benzoic acid solution if the Ka of benzoic acid is 6.5 times 10 to the minus 5. So we're going to need an ice table for this. So this is benzoic acid plus water yields H3O plus benzoate. Okay, note that benzoic acid is a weak acid because it's not one of the 6 or 7 or 8 strong acids that you've learned. All right, so we know the initial concentration of this one. It's 0.461 molar. The initial concentration of H2O doesn't matter because it's not in the Ka expression. The initial concentration of H3O plus is 0, and the benzoate is also 0. What about the change? Well, we know we're going to reasonably lose some amount of this and gain some amount of each of these. Note that they're 1 to 1, so minus x plus x plus x. What is the equilibrium concentration of this? Well, it's 0.461 minus x. All right, we're going to go ahead and ignore this x because x is going to be very small compared to this value. All right, it's going to be 0.000 something. So it's going to be very small compared to this value, so we can ignore it. And this one's going to be x, and this one's going to be x. Now we can write a Ka expression, just like we wrote Kc's for earlier in a problem that was just like this. So the Ka is going to equal the product, H3O plus, that's the one we care about because that's the one that affects the pH, times the benzoate, C6H5CO2 minus the other product right there. So products, okay, over reactants, C6H5CO2H, the benzoic acid. Note we ignore the water because the water is liquid. Now plug in. Ka we know. 6.5 times 10 to the minus 5 equals x times x, or x squared, over this 0.461. When you do that, you find that x squared is equal to 0.461 times 6.5 times 10 to the minus 5, which is going to be 3 times 10 to the minus 5. Now take the square root, and you find that x is equal to, where is it here on my paper, 5.5 times 10 to the minus 3. This is also the concentration of H3O plus. All right, now I don't have enough space here to write this out. So we have found the concentration of the H3O plus, but it doesn't ask us for the concentration of H3O plus. It asks us for the pH. So I'm going to use this space that I find over here. Okay, so I'm just going to make an arrow, very long arrow, that says pH equals the negative log of the concentration of H3O plus, which is going to be the pH, equals the negative log of what we just found, which is 5.5 times 10 to the negative 3, and the pH is going to be equal to 2 point something. Okay, note that this is 5.5 times 10 to the minus 3. If it was 1 times 10 to the minus 3, the pH would be 3, but this case it's 5.5, so it's going to be 2 point something. All right, and when we do that, we find that it is 2.26, which is choice letter A. It is not a particularly easy question. It's a lot of steps, and it's also particularly difficult to fit on this piece of paper in the allotted space. All right, so if you saw the previous question, you saw that I made a bit of a mess trying to fit it all on there. All right, so it says determine the pH in a 0.35 molar NaOH solution. Well, it's important to remember that if you have NaOH solid, it's going to form Na plus aqueous plus OH minus aqueous. Said another way, the concentration of NaOH equals the concentration of OH minus. All right, this is not in equilibrium. So whatever NaOH you have, you get one OH minus. So what we want here is to determine the pH of a solution with a concentration of OH minus of 0.235 molar. So that is the concentration of both OH minus and NaOH. So there's lots of ways to do this. Well, there's at least 2 ways to do this. What I'm going to do is find the POH first. The POH equals the negative log of the OH minus concentration. Whoops. So the POH is going to be equal to the negative log of 0.235. The POH is going to be equal to 0.629. let me write it down again, 0.629. Then the pH plus the pOH is equal to 14. So if you have 1, subtract 14. 14 minus it will give you the other one. So the pH equals 14 minus the pOH, which is in this case 14 minus 0.629, which in this example is going to be 13.37, which is choice letter E. All right, number 21 says, determine the pOH of a 0.188 molar NH3 solution at 25 degrees C, and then it gives us the Kb of NH3, and hopefully I have a little bit more space here in order to do this. So Kb's mean that OH minus is a product, okay, of the equilibrium reaction. For Ka's, H3O plus is the product of the equilibrium reaction. So we know OH minus is the product, but we also know that NH3, hopefully from memory, is a weak base. So it's going to take a proton away from the H2O, and that's what gives us the OH minus. So we end up with NH3 plus H2O yields NH4 plus because it took a proton away from this, plus OH minus. We're going to do an ice table. Okay, this is very similar to the previous problem, number 19, except now we have a base. So let's do our ice table. The initial concentration of our ammonia is 0.188 molar. The initial concentration of the NH4 plus and the OH minus, this is what we care about because it's what affects the pH, are both 0. We're going to lose X of this and gain X of each of those. And we're going to end up with 0.188 minus X, X, and X, and we're going to go ahead and ignore this X because it's going to be 1.188 is going to be way more than, this is going to be way less than 5% of this one. Okay, that's the best way of saying that. So now we can write a Kb expression. So our Kb is equal to products NH4 plus, we don't really care about that one, OH minus, that's the one we care about because that one affects the pH, divided by concentration of NH3. Now, when I say we don't care about it, it doesn't mean we cannot put it here. It just means that we don't need to find this to find the pH. We need to find this to find the pH. Of course, you have to find this to find this. So don't ignore it in the sense that don't put it in the expression. Don't put water in the expression, though, because that's a liquid. All right, now we have our Kb expression. Well, what do we know? Well, we know our Kb. Kb is 1.76 times 10 to the minus 5. Again, KBs have OH minuses in them, or OH minus is a product of the equilibrium, that's the same thing, equals X times X, right? These are both X, divided by 0.188. We're ignoring that X. When we do this, we cross multiply, we find that X squared is equal to this times 0.188, which is going to be 3.31 times 10 to the minus 6. Then we're going to take the square root, and we're going to find that X is equal to 1.18 times 10 to the minus 3. This is the concentration of OH minus. So now we can do exactly what we did in the previous question. We have the concentration of OH minus, and we want to find the pH. Well, the first thing to do is find the pOH, which equals the negative log of the OH minus, which is going to equal the negative log of the 1.18 times 10 to the negative 3. So the pOH is equal to 2.740. And I just realized the question only asks us for the pOH. We don't need to find the pH. If we wanted to find the pH, you just do 14 minus that, and we would have the pH, okay, so it would be, what, 11 point something, all right, but it only asks us for the pOH, which is choice letter E. All right, 22 asks us to interconvert Kas and Kbs. It says determine the Ka of CH3NH3 plus, okay, at 25 degrees C, and it says the Kb for methylamine. This is methylamine, okay, this is methylammonium something, the counterions chloride, methylammonium chloride. So the Kb for methylamine is 4.4 times 10 to the minus 4, okay. So we just need to remember that Ka times Kb equals Kw. All right, and this equation is derived for you in the textbook. It comes from concentration H0 plus concentration OH minus equals Kw. But if you rearrange your Kb and your Ka expressions, you find that Ka times Kb also equals Kw. So this is very similar to converting between H3O plus and OH minus. So the Ka equals the Kw divided by the Kb. If you have one, you just 1 times 10 to the minus 14 divided by the other gives you the other one. So in this case, Kw is a constant, 1 times 10 to the minus 14 divided by the Kb, which is given to us, 4.4 times 10 to the negative 4. And when you do that math, you find that it's 2.3 times 10 to the negative 11, which is choice letter D. All right, question 23 says, which of the following solutions is a good buffer system? So a good buffer should be a weak acid plus its conjugate base, or a weak base plus its conjugate acid. Okay, so these are going to be good buffers, weak acid and conjugate base, or weak base and conjugate acid. So if you look here, you in the first solution, you have a strong acid, okay, and the conjugate acid or a weak base, but you have a strong acid. That's not going to work. All right, choice number 2 is the same thing, or B is the same thing. You have a strong acid, HBr. Strong acids are not going to make good buffers. In letter C, let's take a look. We have a strong base and another strong base. Okay, this would be good for, making Drano, although it's not concentrated enough, but this is not going to make a buffer, okay, because you have 2 strong bases. Now let's look here. We have acetic acid, which is a weak acid. This is the one you're going to use in the lab. And then we have lithium acetate, which is its conjugate base, because it's C2H3O2 minus. Notice the Li plus is just a counterion. You can't put a bunch of acetates in a bottle. You can put lithium acetates or sodium acetates. You need a counter ion. This just acts like a spectator ion, very much like what you're going to do in the lab. So you have a weak acid and its conjugate base, which is really C2H3O2 minus with the lithium plus as the counter ion. So this is our answer, choice letter D. All right, it says a 1 liter buffer solution is 0.05 molars of acetic acid and 0.25 molar sodium acetate. I just realized this will help you solve the previous question. It's sodium is the counterion instead of lithium, but this is a buffer, okay, and it's exactly the answer from up there. But anyway, that's neither here nor there. It says which of the following actions will destroy the buffer? So we have 0.05 moles of acid and 0.25 moles of conjugate base. So if we add 0.05 moles of sodium acetate, that is not going to destroy the buffer. To destroy the buffer, we need to add a weak acid, a strong acid or a strong base. So adding a weak acid, or in this case a weak base, is not going to help you. In this case, adding the weak acid is not going to help you. All right, now in the third example, we have a strong base. What is this strong base going to interact with? Well, this strong base is going to potentially interact with that one, right? Because this is the acid. So if we only have 0.05 moles of this, adding 0.05 moles of this will completely remove this from the system. If this isn't in the buffer, it's not a buffer anymore. It's basically just a solution of sodium acetate, which is not a buffer, sodium and potassium acetate, but that's just a spectator ion. So this is what's going to destroy the buffer. If we add 0.05 moles of HCl, the HCl is going to react with this molecule, okay, the conjugate base. The problem is, if you only add 0.05 moles, you're still going to have 0.2 moles of this left. So if you have 0.2 moles of this left, and only 0.05 moles have been converted to this, you're still going to have a buffer. It will react, but it's still going to be a buffer. So the best answer here, and the only answer here, is choice letter C. All right, it says the pKa of formic acid is 3.74 and the pH of a formic acid sodium formate solution is 3.89. Which of the following is true? Well, don't forget your Henderson-Hasselbalch equation. pH equals pKa plus log concentration base over concentration acid. Okay. In this case, the acid is formic acid and the base is sodium formate. But that's not super important. What's important to remember is the pH equals the pKa plus the base over the acid. What does that mean? Well, it means that your pH and your pKa are related by the relative concentrations of your base and your acid in solution. So in this case, your pKa is this and your pH is higher. Okay, so if you want the pH to be 3.09 and the pKa is 3.74, you want the pH to be higher than the pKa. Well, of course, you have to add more base to make the pH go up, right? The base is on the top. That's important mathematically, but just thinking about it logically, if you want the pH and the pKa are related, if you're familiar with that, then what you need to know is that if you want the pH to be higher than the pKa, more base. If you want the pH to be lower than the pKa, add more acid. If these things are exactly equal, then the pH equals the pKa. All of this comes out of the Henderson-Hasselbalch equation, but logically, we simply want to add more base. So let's take a look at our answers. The HC2CHO2, or acid concentration, notice the H is a giveaway of the acid, okay, and the Na is a giveaway of its conjugate base. So if we look at this, the HCHO2, the acid concentration, is less than the base concentration. That's what we want. If the two things are equal, the pH equals the pKa. All right, because if these two things are equal, you have the log of 1, and log of 1 is 0. In this case, the acid is greater than the base. That's not going to work. And in this case, the acid is much greater than the base. That's not going to work. It only works when the acid is less than the base because the pH is higher than the pKa. I hope that makes sense. All right, so the next few questions are pretty difficult. It says calculate the pH of a solution formed by mixing 100 milliliters of 0.2 molar HClO with 200 milliliters of 0.3 molar KClO. Okay, and then it gives us the Ka value for this, but we actually need the pKa, so we're going to take the negative log of that, and we're going to find that it's 7.54. So the pH is equal to the pKa plus the log of base, in this case KClO, over acid, in this case HClO. Alright, so this is going to be our expression. The problem is we mix two liquids together. And whenever you mix two liquids together, you're going to have a change in volume. And whenever you have a change in volume, you're going to have a change in molarity. Okay, so this is important to be aware of. So what we need to do is we need to account for that. So the first thing we want to do is we want to find the concentration of HClO in the final solution. To do that, we're going to use C1V1 equals C2V2. So the initial concentration of this is 0.20 molar times the initial volume of it we used is 100 milliliters. C2 is what we're trying to figure out. And then V2, oops, I don't want to write V2. The V2 is the total volume, 100 plus 200, or 300 milliliters. When you do that, you find the C2 is equal to 0.067 molar. We need to repeat that for KClO. So the concentration of KClO is going to be exactly the same thing. C1V1 equals C2V2, where C1 is 0.30 molar. The initial volume of that one we used was 200 milliliters. C2 is still what we're looking for, and V2 is still 300 milliliters because we mixed them together, and it might be 300.0. That's not a big deal. C2 is going to be equal to 0.20 molar. Now we have the concentrations in the actual solution. So again, we had to find the pKa by taking the negative log of the Ka. The pH equals the pKa, which is 7.54, plus log of KClO concentration, 0.20, divided by HClO concentration, 0.067. Note that the pH has to be higher than 7.54. Why? There's more base in the solution than acid. So when we do that, we get that the pH is equal to 8.01, which is choice letter C. All right, it says a 1.5 liter buffer solution is 0.25 molar in HF and 0.25 molar in NaF. Calculate the pH of the solution after the addition of 0.1 moles of solid NaOH. Assume there's no volume change. And then it gives us the Ka for HF. Now, in order to solve this, we can't use the Ka. We're going to need the pKa, so we need to take the negative log of that. So the pKa of this HF is 3.46. Okay, or the pKa of HF is 3.46. So we know now the pKa of this thing. So that will help us if we plug into the Henderson-Hasselbalch. So pH equals pKa plus log of NaF, or F minus if you prefer, over HF. Okay, so this could be F minus as well. So this is the same thing. So this is just a spectator ion. All right, but when we first start, the pH is 3.46. Why? Because these two concentrations are exactly the same. So if these two concentrations are exactly the same, then we take the log of it, it's going to be 1, or excuse me, it's going to be 1, and then the log of it is going to be 0. So the pH is going to be equal to the pKa. So when we start, the pKa is 3.46, or the pH is 3.46. Then it's going to go up. How's it going to go up? Well, we're adding NaOH. If we add a base, it's going to be higher. So the possible answers are this one, and this one. These two answers are not possible because we would have to add acid in order to get the pH to go down, and the pH is going to go up. So we got a 33% chance if we just guess right now. But let's actually solve this out. Okay, so the first thing we need to do in order to solve this out is we need to find the concentration of the NaOH. So the concentration of NaOH is going to be the moles over the liters, which is going to be equal to the number of moles, 0.100 moles, divided by the number of liters, which is 1.5 liters. And when you do that, you find that the concentration of the HF is going to be equal to, sorry, I have it over here, it's 0.0667 molar. Now, the HF is going to react with the NaOH to form more NaF and H2O. So this is kind of like an ice table, but I'm going to call it like a before, change, and after, or before, reaction, and after. So before, change, after, something like that. Okay, because it's not an ice table, because it's not an equilibrium. So it can't be an equilibrium. So in this case, the initial concentration before we do anything of the HF is 0.250 molar. Okay, the initial concentration of the NaOH is 0.0667 molar. This is for the magical time when you mix them together, but they don't react. Okay, the time that probably doesn't really exist. I guess it does exist. It's just very, very short. All right, then we have NaF. All right, the NaF concentration before we do anything is 0.250 molar. Then these things are going to react. So if you want to be or A, it doesn't matter. All right, I'm going to have a change. Well, what's going to happen? These two things are going to react to form more of this. And since we have more of this than this, we're going to run out of this first. So we're going to subtract 0.0667 molar of this. We're going to subtract 0.0667 molar of this. But where does this go? Well, this goes, these two react to form more of this. So we're going to gain 0.0667 molar of the NaF. So these two react to form more of this. We're also going to get more water, but that doesn't matter because water is not in our expression, so we can just leave it alone. All right, when we do that, and we do this subtraction, we find that what's left of this is 0.183 molar in concentration. What's left of this? None. Okay, and what is left of this is 0.317 molar. Note that if there were NaOH left over, all right, and we ran out of HF, then the pH would just be based on the concentration of the NaOH, because this is a strong base, and this is a weak base, and you're not going to have a buffer anymore. All right, but in this case, we ran out of the NaOH first, so now we have our after the reaction conditions. So we can find that the pH equals the pKa, which we found a minute ago by taking the negative log of the Ka, 3.46, plus log of NaF, which is 0.317, divided by HF, which is 0.183. And when we do that math, we find that the pH is going to be 3.69, which is choice letter A. Okay, so that is a pretty tough question. All right, it says titrating a weak monoprotic acid with NaOH at 25 degrees C, the pH will be. So it asks us something about the pH at the equivalence point. So if we look at this, if we take a weak acid, HA, and we titrate it with NaOH, at the equivalence point, the HA and the NaOH are equal. So what's in solution? NaA, or A minus, and H2O. Na is just counter ion. So we have A minus in solution. This is a weak acid. This is its conjugate base. So what do we have in solution? What we have in solution is the conjugate base of a weak acid. Well, the conjugate base of a weak acid is going to have a pH greater than 7 at the equivalence point. Why? Because it's a base. So it's going to react A minus plus H2O is in equilibrium with HA and OH minus. So you're going to increase the concentration of OH minus in solution, or said another way, you have the conjugate base, so the pH is greater than 7. So the answer here is choice letter D. All right, so we have another titration. It says a 100 ml sample of 0.1 molar HClO4, this is a strong acid, is titrated with 0.27 molar lithium hydroxide, this is a strong base. Determine the pH of the solution after the addition of 30 milliliters of LiOH. So very much like in number 27, we need to find the concentrations of things. So in this case, we need to find the concentration of HClO4 and the concentration of LiOH, and we're going to do this before, change, after type of thing. So the magical time when you mix the two solutions together but they have not reacted, the change in concentration, and then what you have after it, so we can determine the pH. So the concentration of HClO4 is going to be determined by C1V1 equals C2V2 because we've diluted it, right? We started with 0.18 molar and 100 milliliters of it, and we added to it 30 more milliliters. We want to find C2, but we have a total volume now of 130 milliliters. When you do that, you find the C2 is equal to 0.138 molar. So before they react, we have 0.138 molar HClO4 because we have diluted it. The concentration of LiOH is very similar. Okay, the initial concentration is 0.27, so that's C1, times the initial volume. This one we only added 30 milliliters of. C2 is what we're again looking for, and the total volume is again 130 milliliters because it's the same solution. When you do that, you find that C2 is equal to 0.0623 molar. So we're going to have 0.0623 molar of this one. Now, we need to figure out which one's going to run out first. Since they react in a one-to-one relationship, the one that's less is going to run out first. So we're going to lose 0.0623 molar of this, and lose 0.0623 molar of this. Why? Because this one is less than this. So this is going to be gone, and we're still going to have some of this left. Some of the acid specifically left. When we do that, the concentration of this one is 0.076. I guess it should be 0.0757 molar. And this one is 0. There's none left because we used it all up. Well, now we just have a strong acid in solution. So the pH equals the negative log of the concentration of H3O+, but the concentration of H3O+ is equal to the concentration of HClO. because it's a strong acid. So negative log of 0.0757 molar. And when you do that math, you find that the pH is equal to 1.12, which is choice letter B. All right, so if you haven't watched the few previous problems, it's probably better to start with those because this one is the most complicated. It says, if a sample of 100 milliliters of 0.1 molar ammonia is titrated with 0.1 molar HNO3, determine the pH of the solution after the addition of 60 milliliters of HNO3, and then it gives us the Kb of NH3. So, when we do this, there are several things to keep in mind. In the previous example, in question 29, we had a strong acid and a strong base. So they simply just neutralize each other. They weren't able to completely neutralize each other, which is why we had a very low pH, but they did neutralize each other. In this case, we have a weak base interacting with a strong acid. This means that we could end up with a situation where we have some ammonia in solution and some NH4 plus in solution. Said another way, we have a buffer. Or we could end up with a case where we just have strong acid in solution. So basically, if we have more of this than this, we just have a strong acid solution. But if we have less of this than this, then we have a buffer because we're going to have both of these in solution. So this is more complicated than the previous example. The first thing you need to realize is that we're eventually going to need, well, maybe we won't, so let's do that after. I was going to say we eventually need a pKa, but if it's not a buffer, we wouldn't need that. All right, so let's take a look. We still have this dilution problem that we had in the previous few questions. So we have the concentration of NH3 before the reaction, but it gets diluted, C1V1 equals C2V2. The initial concentration of NH3 is 0.10 molar times the initial volume, which is 100 milliliters, equals C2. What is that? All right, C2 times V2, which is going to be the total volume of the solution, which in this case is the 100 milliliters plus the 60 milliliters of the HNO3, so 160 milliliters. When you do that, you find that C2 is equal to 0.0625 molar. Okay, so this is the concentration after. We need to repeat this exact same process for the HNO3. So the concentration of HNO3 after they're diluted, again C1V1 equals C2V2. Again, it's 0.1 molar to start with. But this time we only added 60 milliliters of the HNO3, so we're going to multiply by 16 on 100. C2 times the total volume is still 160 milliliters. And when you do that, you find that C2 is equal to 0.0375 molar. All right, so now we know the concentrations of these things after mixing before they react. So we're going to call that before. So this one is 0.0625 molar, and this one is 0.0375 molar. And the initial amount of ammonium is 0. We don't care about nitrate, it's just a spectator ion. So let's take a look. It looks like we're going to run out of HNO3 first. Why? Because there's less HNO3 than there is NH3, and they react in a 1-to-1 ratio, so we're going to run out of this first. So we're going to subtract 0.0375 molar here, and subtract 0.0375 molar here. When you subtract these two numbers, you find that this is 0.0250 molar, and this one is 0. But we missed something. What happens when these two things react? They form this and this. So we're actually going to gain 0.0375 molar of this. And we're going to ultimately have 0.0375 molar ammonium in solution. Because of this fact, we're actually going to have a buffer. It's going to contain a weak base and its conjugate acid. So pH equals pKa plus log the concentration of base, NH3, divided by the concentration of NH4 plus its conjugate acid. But we have a Kb. We can find the pKb by just taking the negative log of the Kb, which is going to be 4.74. We could find the pKa by taking 14 minus the pKb, which is going to be equal to 14 minus 4.74, which is going to be equal to 9.26. This is the pKa of the ammonia. So now we have, well, actually the NH4 plus, but now we have the pKa. Now we can plug in pH. I think that's the ammonia. Sorry about that. The pH equals the pKa, which is 9.26, plus the log of the concentration of NH3, which is 0.0250 molar, divided by, we don't really need that, 0.0375. So in this case, you're going to have slightly more of the acid than you have of the base. So this means that the pH is going to be slightly lower. And when you do that, you're going to find that it's 9.08. Okay. For some reason, I have this here as 9.44, but I'm going to change that to 9.08, and the answer will be choice letter B. So on the version that you see, this will say 9.08, which will be choice letter B. All right, this was quite a long video, and I thank you for watching. There are some hard questions on here. It's very important that you practice, so thanks for watching.